Okay, so let's get started. For those of you who have actually been looking at Moodle, there is a quiz that we have put up. Okay, so this is mostly meant for the section 2, the people who don't come to class. They have to view the recorded lecture. The incentive for them to keep up, we have put out a quiz, but for those of you who are in section 1, you should also complete the quiz. That's encouragement for you to pay attention in class, okay, and not follow what's going on. So do go take a look at Moodle. What we plan to do is every week we will give a quiz on Wednesday, due by Sunday. Okay? The aggregate points for the quiz is very small, so don't worry if for some reason you forget or you're not coming to class, but this is mostly meant as a way for everyone to keep up. There will be real homework. The quiz is just a multiple choice thing. It should take less than 10 minutes or 5 minutes really to finish. Okay, so keep an eye out for that. You will also see on Moodle there is a link to a system called Piazza. I don't know if anybody here has actually used it. Okay, that's a question answer forum which we are going to use for this class. The number of students is, as you know, around 60. So just so that we can provide answers to questions rather than you have to come to my office or the TA's office just to ask simple questions, you can also use the forum. So please go sign up on Piazza and then sign up for 677. Okay, so those are the two administrative announcements. Let's continue the lecture from where we left off. So there are a few slides we couldn't finish last time. I'm going to finish those first and then we will switch to chapter 2. So keep in mind that we are proceeding at a steady clip. We have already completed one chapter from the book, or we will shortly complete the first chapter, and we are going to move on to the second. So please keep up. I know it's very early on in the semester, but please keep up with the material, okay, because we are going to keep covering a chapter every 2 or 3 lectures. Yeah, so last time I provided an introduction to distributed systems. I gave you some advantages and disadvantages of distributed systems. Towards the end of the class, I started talking about operating systems, okay, and then wanted to give you the evolution of operating systems, different classes of those. We have talked about uniprocessor operating system so far, okay, in the last class. So now let me tell you a little bit about what distributed operating systems are. Okay, as the name suggests, it's an OS that runs on a collection of machines that are cooperating with one another to implement some sort of a distributed system. Okay? So the goal here for the OS is to manage all the resources in a distributed system. Okay? In a uniprocessor operating system, the kernel manages the hardware resources on that machine alone. In a distributed OS, the kernels, well, there's one running on each machine, the kernels collectively manage the resources on all of the machines. Okay? And in the pure form of a distributed OS, you basically provide a seamless and transparent view to the user of all the machines. Okay? The presence of either machines are sometimes even hidden from the user. It just looks like one large logical machine that's a collection of physical machines. Okay? So it looks to the user as a centralized OS. It provides transparency, as I mentioned to you. The transparency is a property where you hide certain aspects of the system from the user. A distributed OS provides even machine level transparency. You don't even know there are multiple machines. All the machines act like one single logical machine. Okay, and presents essentially a uniprocessor like abstraction as far as interaction goes and provides transparency. Okay. I'll show you a picture in just a moment, but there are two other types of operating systems that we will look at. Okay. The definition of a distributed OS that I just gave you is what we would call a pure distributed OS. Okay. Typically what you see in practice is not that abstraction, but something that's looser form of a distribution. Okay. So what you get really is either what is called a network operating system or a NOS or a middleware layer that allows you to construct distributed application. Okay. So a distributed operating system in its purest form is tightly coupled. Okay, tightly coupled OS kernel that runs on multiple machines or multiprocessors hide the presence of multiple processors from the user. Okay. A network operating system is a loose form of coordination. Okay. You have an independent kernel that is running on each machine, and the OS provides functionality that allows machines to communicate with one another. Okay? What you have in practice today, whether it's Windows, Mac, Linux, any form of Unix, is essentially a network operating system. Okay? The presence of other machines is not hidden from you. You have to explicitly use SSH or some other mechanism to log into other machines in order to access files or run applications. Okay? The OS is not hiding the presence of other machines from you. Okay? Yet it is providing functionality for you to communicate with other machines, log on to other machines, use resources from other machines. Okay? That's called a network operating system. Okay? And what you can build on top of a network operating system is a software layer called a middleware layer that can provide better functionality. And I'll show you some pictures of what that does. And in particular, you can provide some form of transparency by building this layer on top of the network operating system. Okay. Now, I will distinguish the term multiprocessor operating system from a distributed operating system. Okay. So we have uniprocessor operating system. That's a kernel that runs on a machine with one processor. If that machine has more than one processor or more than one core, you essentially have a multiprocessor or a multi-core operating system. Okay? The multi-core operating system, basically you still have one machine but more than one processor. And typically in this case, the presence of the multiple cores is hidden from the user. Okay? You may have a laptop that has more than one core. Okay? You do not work with that laptop any differently than if your machine had only one CPU. Okay? Typically, you just start jobs. It's the job of this operating system kernel to figure out which application to run on which core and so on. You don't start a process and say, run this on core 1 or core 2. All that is hidden from you. The OS takes care of that for you. Right? So in a multi-core or a multi-processor environment, there's more transparency. The fact that there is more than one core is hidden from the user. But not so in the case of a network operating system. Okay, so here is essentially an example of what is called a MOSIX. This is like a case, a small case example of what is called a MOSIX operating system. This is essentially a cluster-based operating system kernel that runs on top of multiple machines. So it's built using Linux, but it provides an abstraction of what is called a single system image. Okay, so you have essentially in this case a set of machines shown by a box. Each machine runs a kernel. Okay. And then there are distributed operating system services that run on top. That's essentially the MOSIX layer. And that MOSIX layer essentially hides the presence of multiple machines. Okay. It looks like one large machine. So you can go to any machine, submit a job, okay, start a process, start an application. MOSIX figures out which real physical machine is going to run it for you. Okay. You don't actually have to log on to machine 10 and run a job on there. You can essentially submit a job and the OS is going to figure out where to run it and so on. Okay? So it's typically meant for large clusters where you run batch jobs. So you may have 100 nodes and you are just using these nodes to run computational jobs rather than asking the user to figure out, find the least loaded or an unused machine and run the job there. Okay? The OS is going to take care of that for you. There's a scheduler in there that will figure out what machines are in use, which ones are not, if new jobs come in, where to run them and so on. Okay, this is just one example. Okay. This picture here shows you a network operating system. Okay. This is what the world looks like for most general purpose operating systems. There's Windows, Mac, Linux. You have your kernel. Okay. This is no different from what either a uniprocessor or a multi-core kernel looks like. And then the OS also provides you what are called network services. Okay, it will support a TCP/IP protocol stack. It will support protocol like SSH, FTP, SCP, all of these protocols that allow this machine to work in the network, okay, whether that's a local area network or internet. So the users use these services to run any distributed application, whether it's using your browser to browse the web or whether it's using FTP protocol to transfer files. All of those protocols are enabled by functionality provided in the kernel to enable the machine to be networked. Okay? The important thing to realize is there is no transparency being provided here. You have to be explicitly aware of what resources you are accessing and what machine they are on. Okay? You might have to explicitly SSH onto a machine, let's say the Ed Lab machines, okay, to compile your programming assignment and so on. Yes, there's a question there.
So this is somewhat specific, but something like
Okay, there's a question about Sun Grid Engine where you submit jobs. Just hold on for 1 second. I'll go to the next slide. It is a middleware, and I'll show you what that means in the next slide. Okay, and we'll come back to that question. We'll just defer that for just a few seconds. Okay, so this is basically another picture that shows how a network operating system fits into the bigger picture. So each machine here is running a network operating system. You can use these NOS machines to run client server application. What is being shown here is essentially a network file server where there is one machine that has lots of disk space where files are stored. These are client machines that also run, all of these run a network operating system. So you can essentially request files from the file server, access them, read them, write them, and so on. Okay, this is just showing how you can use the network OS concept to build distributed applications. Okay, now I'll come back to that question that was just asked. So here is how you build a middleware. Okay, so a network operating system provides the building blocks for applications to be written, but it doesn't provide any functionality where it's convenient for you to write your application. You still have to be aware of the presence of machines. You have to do all the low-level plumbing, the networking, all of that has to be done by the application designer. If you wanted to simplify that task, what you could do is you could write a layer, software layer that sits on top of the network operating system. This layer would implement important functionality that user doesn't have to deal with anymore. The middleware layer will take care of that for you. Okay, there's an example just given here. We can just use that example to understand what this means. So let's suppose that you go back to a cluster scenario where you have a set of nodes and your user submitting computational batch jobs. Okay, if you had a pure network operating system, okay, like this, then you would have the user. It would be the burden of doing this would be on the user, where each user would have to come in, figure out which machine to choose to run his or her job, explicitly log on to that machine, submit that job, and then wait for the results. Okay? And now if there are lots of users, how to coordinate this, all that is left to the user. The OS is not doing, OS is only providing you computational resources. Okay? You, the user, have to figure out which machine to use. Okay? Now, what a middleware can provide, you can take this abstraction and say that's not convenient. Okay? We don't want to let users figure this out. Let the system figure it out. Okay? So you could then build a middleware layer on top where all you have to do is you submit your job to the system, which is the entire cluster. This middleware layer will keep track of the load on each machine, the utilization on each machine, what jobs are running, and when a new job comes in, it decides which machine to send that job to. Okay? And it basically executes that job on that machine and returns those results. Okay? Notice that the OS did not provide that functionality for you. Somebody else has come in and built a layer on top of a network operating system to provide that functionality. Okay? Now, Sun Grid Engine is essentially a middleware layer that does exactly that. That was originally built by Sun. Now it's an open source software. Okay? It allows you to take a cluster. That's a middleware that you run. Okay, it's a batch scheduler, distributed batch scheduler. You come submit jobs, it will figure out where to run it for you. So that the inconvenience that a pure network OS had presented to the user is gone. Okay. Now, in the Mosaic scenario, the OS, that functionality that the middleware was providing was actually built into the OS itself in some level. Okay. In this case, it's built outside the OS by a middleware. Okay. So what the point here is that depending on where you put that functionality, whether it's in the kernel or outside, you can get a network operating system, a middleware operating system, or a distributed operating system. Okay, from a functionality point, they do more or less the same things, but things are implemented in different places. Yes, Sandeep.
So distributed batch jobs and single machine batch jobs. So in other words, like what sort of services does the middleware provide for distributed applications or distributed batch jobs as such?
Okay. What kinds of functionality? Question is, what kind of functionality does the middleware provide for distributed batch job? Right. We are going to come back. I'll give you the short answer. We are going to come back to processor and distributed scheduling for chapter 3. We'll look at this in a lot more detail as to how this is built. Okay, this is just an introduction, but to answer your question, the kinds of services a middleware would provide is communication across nodes. Okay, so if you want to have not one batch job, but a set of batch jobs running that have to work together to implement some higher level application. The middleware would provide you lots of functions like inter-process communication. One component can send messages to another component through the middleware. It will allow you to do automated mapping of jobs to machines. Okay? It will allow you to do naming. It could provide you other services like distributed locks. If you want to have concurrency and synchronization, it could provide you synchronization services and so on and so on. SunGrid engine doesn't do that. You need other middleware to do that, like Corba. We'll look at all of that as we go along. Okay? It depends on what kinds of application you want to support. If it's a pure batch job, you really are only looking to decide where to run the job. Okay? You are not even providing inter-process communication services. If you have anything more sophisticated, you can have scheduling, you can have inter-process communication, locking, transactional services, whole set of them. Okay. Any other questions here? Okay, that's basically leftover material from last time. I'm going to now switch to today's lecture. Okay. So we are going to continue our broad brush introduction to distributed systems, but go a little deeper today. We are going to look at broadly architectures for designing distributed systems. This is chapter 2 of the book. So we'll look at centralized, decentralized, hybrid, middleware-based, peer-to-peer, self-managing. So a whole slew of these higher level concepts. Okay? And after this introduction, next time we are going to actually start the first real topic, which is communication in distributed systems. Okay? This is still introduction, but a little more in-depth than what we did last time. Okay? So let's look at architectural styles. Okay? The reason we want to understand this is when you build your application or your system, you need to decide what architecture you are going to employ for your application or system. Okay? So we are going to look at several layered, object-based, data center-based, driven, event-based, and so on. Let's start with the layered approach. Okay? So it's a very high level. Okay? So we'll then dig a little deeper. So here is a layered approach for designing a distributed application. So in this case, you take your application, you partition the functionality into layers. Okay? Layers are stacked one on top of another. Okay? We are going to layer the numbers 1 through n. Okay? And the way you build your application is each layer can only communicate with the layer above it and the layer below it, no other layer. Okay, so layer I, you have to construct your application, okay, such that layer I can only talk to the layer above it and the layer below it. Okay. So if you build your application in this fashion, this is called the layer design for building your application. Okay. Now, what each layer is essentially doing is taking the functionality that is provided to you by the layer below it, adding some new functions and exporting a higher level function to the layer above it. Okay. Now those of you who have taken any networking class, you will realize that this approach closely follows the protocol stack that you also see in the network protocol stack, the TCP/IP stack that you also see in operating system kernels. Okay, so if you look at the protocol stack, you have basically the physical layer, the MAC or the data link layer, the network layer, transport layer, and so on. Okay, each layer there also has the same constraint. You can only talk to the layer below and the layer above it when you do packet processing. Okay? You can build distributed applications in the same way. Okay, so the thing that's not allowed, okay, if you did not impose the structuring, you just had components, you will allow any component to talk to any other component. So we have put constraints on that. Okay, each component can talk to at most 2, the component or the layer above and the layer below. Okay, now where is this kind of design used? Okay, it turns out that this is a very popular way of designing many distributed applications. We'll look at this, what is called multi-tier web application. Okay, this is how most the simple web application, not complex ones. Simple web applications are designed when you essentially have a server, okay, like it's an e-commerce site or any other form of server. This is essentially how it is designed, and we'll look at that in a little more detail shortly. Okay, so let's do all the styles and then we'll come back to multi-tier. Okay, here's another way to design your distributed application. This is an object-oriented approach. Okay, so you take your application. Okay, you take its functionality and you partition them into objects. Okay? And then objects export interfaces and methods, and any object can call a method on another object. Okay? Now at this level, this looks very similar to writing essentially a Java application. Okay, your classes, when you run your app, your classes get instantiated into objects, objects call methods on one another, and the application as a whole does its job. Okay? In a distributed application, the main difference is that objects, not all objects are going to reside in a single address space or even on a single machine. Okay? Different objects or collect groups of objects may reside on different machines. Okay? You are essentially invoking methods on objects that reside on another machine. And this is typically done through what is referred to as remote method invocation, RMIs. Java supports RMIs, so you could take write such an application in Java. Okay? So this is an object-oriented approach to writing distributed applications where objects could reside on independent machines. They export methods, and you can invoke a method on an object that doesn't reside on your machine, it resides on some other machine. Okay? Again, how to do this we will come back to when we talk about communication. This next chapter we'll look at this in quite some detail. Okay, your first programming assignment will involve some flavor of this as well. Okay. So you essentially are using RPCs, remote procedure calls, which in the object-oriented worlds are referred to as Java RMIs, or not Java RMIs, RMIs. Okay. Very popular in client-server systems. Okay. So this form of programming. Now the important thing to realize is here we are not imposing any restriction on which object can invoke methods on which other objects. We allow any object to invoke methods on any other object. Okay. In layered design, which you could also use object-oriented techniques, if you basically combine the two, then objects can only invoke methods on objects that reside in the layer above and the layer below. Okay. That restriction in the general case is not present here. Okay. Next technique is called event-based architecture. Okay. We will come back to event-based and the next one, which is blackboard architecture, at the very end of the course. Okay. When we are in lecture 22 or lecture 23, I'm going to remind you that we thought about this in lecture 2. Okay. So we'll have to put this on the stack and then come back to this very late in the course. But I'll describe what this architecture does. Okay. Here, your application is partitioned into components, and components interact with one another. But what is interesting is that there is something called an event bus, where you publish events and you are basically given events, and then you use events to basically communicate. Rather than sending explicit messages, communication occurs through this notion of events, okay, that are sort of more interrupt driven. Okay. A very popular way of using this event-based architecture is to use what is called a publish subscribe or a pub sub paradigm. If any of you have heard of this term pub sub, that essentially means publish subscribe. So what happens here is components will publish an event or a data item. Okay. It will flow through the event bus, and any other component that has requested it or subscribed to it will receive that data event or data item. Okay. This is essentially how communication is going to take place. If this is not very clear, don't worry about it. We are going to spend essentially a class or two, entire class on understanding how event-based architectures are implemented, how publish subscribe work, where they are used, and so on. Okay. Different technique, right? So for implementing your application. The last one we'll talk about is what is referred to as a blackboard architecture or a shared data space architecture. Okay, this is yet another technique to design distributed application. This is probably the loosest form of communication that you will see to designing your application. So here what happens essentially is there is something called a shared data space. Okay. And there are again applications are partitioned into components. Components will, and the important thing is, this may not be clear as to why, but the important thing is they are decoupled in space and time. Okay. So what happens is a component can go and publish something onto the shared data space. At some later point in time, loosely coupled, some other component can come and take whatever you have published and do something with it, the message that you publish. Okay, the best way to understand this is to think of a real physical board, a bulletin board that you will see. Okay, let's say that you are moving and you want to sell some furniture. Okay, now you don't know who is going to buy from you. So you cannot explicitly send a message to the interested buyer saying, here I have this furniture, do you want to buy it? Okay? The only thing you can do is you can publish post a note on this bulletin board saying, I'm moving, I have this furniture to sell. If you want to, if you're interested in this, call me at this number. Okay? You just post this and you go away. Okay? And then people come, they look for things on this bulletin board, and sometimes you may have find an interested buyer who comes and looks, I'm interested in furniture, here is this person who's selling it. So then you go and take that message, and basically you can then communicate with the interested party. Exactly the same thing happens here. Okay? You are essentially sending messages, but you don't know who this message is for. You just post it on this blackboard, and at some later point in time, some application is going to, or component is going to come and take that message from you. Okay? The reason this is called loosely coupled is in all the previous forms of architectures, whenever you send a message, the recipient is well known. You send a socket call, message to someone, you make a RPC call or a RMI call to any entity, and those entities are actually going to know, you address it to that entity and those entities receive it. In the blackboard architecture, you do not have a recipient know that you know ahead of time. You just post a message, and whoever is interested in it comes and picks it up. Okay? Any questions on this? Okay. Now the reason this is interesting is it allows you to enable communication in systems where you do not know what the environment looks like. A very easy example is you basically go into a network somewhere. Let's say you go and join a Wi-Fi network, a new Wi-Fi network. You want to print something to a printer. Okay? Typically, you need to know what the IP address of that printer is and so on, and configure it on your machine so that the printing can be enabled. In a blackboard form of architecture, what will happen is a printer will essentially advertise itself by posting a note to this blackboard saying, I am a printer. Okay, I'm color printer, I'm HP model XYZ. If you want to print, take this information and send me a job at this address. You'll just post that note there. Okay, so you walk into this Wi-Fi network with your laptop and you say, I want to print. I don't know where the printer is. Let me look. Okay, so you just go to the blackboard saying, is there a printer available? And then you look for a message that says, I'm a printer. And then you pick that message and say, here's a printer. I've automatically discovered a printer. Okay, and say, now I'm going to just print to it. And basically, you know the model, so you can basically configure that model on your machine and send a job to that printer. Okay. So this is called form of self-discovery. If you have distributed systems where you can dynamically discover components and enable communication, this is basically the architecture to use. Okay, the printer didn't know ahead of time who was going to print. It basically just posted a note, and then some other machine came along and discovered that node and sent it a job. Yes, question.
You see that this is then a relaxation of the pub-sub model.
Is this a relaxation of the pub-sub model? It is somewhat of a yes, pub-sub. There is some overlap between what a publish-subscribe does and what a shared blackboard architecture does. In this case, there is more decoupling. Right? Even in the pub-sub model, messages that are published, you look for subscribers and you immediately deliver them. Here, messages may sit on this blackboard for hours, days, weeks, months, okay? And at some later point, whenever there is a match, you deliver it. Okay? So in that sense, it is indeed a relaxation. Yeah, there's more tight coupling in a publish-subscribe than here. Any other questions here? Okay. So now we are going to jump into a little more concrete architecture. That's sort of the higher level, broad brush overview. So we'll start first with client server. Then we're going to talk more about multi-tier and so on. So client server model, as you have probably heard of the term client server, very popular way of building a distributed application. You take your application, partition it into a client and a server. Okay? The service or the main function of the application is provided by the server part of the application. Clients simply make requests to the server, okay, access that service and get back a response. So this could be a file server, print server, web server, doesn't matter, mail server. Okay? Every application you can think of, popular one, either falls into this, mostly falls into this client server architecture. Some will fall into what's called a peer-to-peer that we're going to look at also shortly. Okay? Very common style. Okay, the figure there shows how client server architecture works. There shows one client, one server, that's time. Client does some is running. Okay, that's the black line. At some point it sends a request to the server. The request comes over a network to the server machine. Okay, so then server machine processes that request, that's here, generates a reply, sends back a reply. Okay, so this could be a web server where the client is a browser, server is a HTTP server, for instance. Okay. Now, what we are interested, so first of all, you should realize that by making the application client server, you are already distributed. Clients are on one machine, servers are on another machine. Okay. But what's more interesting is what I've called a server is typically also not a single machine. The server itself will tend to be distributed, and that is what we are going to look at. So in particular, the service that the server provides may not actually be one component. It could be a distributed set of components that collectively implements the server. If you think about what a server needs to do, there are three key tasks that any server actually has to do. It has to provide some user interface, or an API that accepts requests. It has to implement the actual processing of the request, which is the real application logic, and it may optionally store some data that these requests are accessing. So in some sense, you will have these three layers that you will see in typical server application. There's the interface part. That's the part that communicates with the client. There's the actual processing. When a request comes in, depending on the type of the request, you may have to do some processing. And requests may also need to access data, so there is a data layer as well. So let's look at that in a little more detail. We'll start with an example of a search engine. This is basically a much simplified example that shows you the three layers in a search engine. So here you are basically, this is the server part of the search engine. You eliminated the client part, which may be a browser, or it could be just a front end that submits keyword searches. So at the very top, you essentially have the user interface level. This is the abstraction that the search engine has exposed to end users. This could be an RMI interface. It could be exposing a JavaScript API that allows you to send the request using JavaScript. So there may be many different ways to implement that interface. So that part of the search engine is responsible for communication. It could be simply an HTTP server that is receiving your search queries over HTTP, the protocol HTTP. And there are many ways to implement that top box, but that's the user interface layer of your server. This is the core of the search engine. These boxes in the middle are the core. So there are many different functions there. So when a request comes in, these are keyword searches. You take those keywords and you have to generate a query. And so you take the request, you construct a query. You will then send that query to essentially a database. This is the database of all the pages this search engine would have crawled and indexed. So there will be an index here with all of the content. So you send off the query, it goes to the database where you have indexed web pages. Your query is going to return some results. Then you might have a ranking algorithm that says these are all the matches. Let me sort them in order of relevance so that the most relevant search results are at the top. So the ranking algorithm is also part of the processing. So you'll take the rank ordered list. You will take the content or snippets of each web pages that you also retrieved from the database, and then you will construct an HTML page using all of those results. And then that HTML page is going to get sent back to the user interface layer. And the user interface layer will then send that back to the end user, client. And then you'll see the results of your keyword search. So this database where you have the index of all the pages you have crawled and the content, so that's the data layer. All of this processing is essentially the processing layer. And the top is the user interface layer. So this should now indicate to you that what you think of a server is typically not one entity. It's more than one. Okay, now this figure doesn't actually show you that each of this could run potentially on a different machine. Okay, this is just showing you the layering. But what also happens many times is that each of those layers may run on a separate machine or even sets of machines. This could be not one database, but it could be a large set of machines that collectively have indexed all the pages for you. Each of this could be one or more machines. Okay, so all these machines have to coordinate with one another to implement this server application. Any questions on this? Okay, so I'll show you some other. So this is a search engine architecture with 3 layers, okay, which is very common. Okay, so that basically that example should now illustrate this notion of a multi-tiered architecture. Okay, so you have a client on the one end, server on the other, okay, and then the server essentially has more than one tier. Okay, the tier is same as a layer. Okay, this was basically 3 tiers. So this essentially, now if you think about it, this is layered design. Okay, what I showed you, although it may not have been obvious, is a layered design. The user interface layer only talks to the processing layer. The processing layer only talks to the database layer. You will never see a request directly going from the user interface to the database. It has to flow through the processing layer. Okay? So this is only 3 layers, okay, so it's somewhat simple. So, but each layer is only talking to the layer above and the layer below it. Okay, yes, question.
Does the layered architecture allow for like two-way communication between neighboring lines, or just in the way that the arrows in the diagram indicate?
Yes, the layered architecture, as you will see, is essentially two-way. There's an arrow going down and an arrow going up. Okay? Typically, the database is not going to just asynchronously retrieve something and give it to the layer above it without a request asking for it. Okay? So all of the processing and the communication is triggered by requests that come in at the top layer. That request trickles down the layers and triggers some functions or retrievals, and then the replies actually trickle up.
So this is kind of a ridiculous example, but if the database got a query request and then needed, I don't know, some sort of like clarification or something, could it send a request back up and then your response?
Yes.
Okay.
So if the database needed some additional information to process, it would trigger another request. But in a typical layered architecture, that module wouldn't necessarily be there. It may be somewhere else, for instance. But yes, it's not. So you could basically, the database itself wouldn't do that. Typically, that logic would be somewhere here. Right? So your request comes in, you say, are you logged in or not? Right? So you basically, like sometimes you may send a request to, let's say you go to Amazon. Right? You say view my order history, request comes in, Amazon is going to send back saying please log in. It doesn't come all the way to the database, it's come here and it's just gone back. Not all requests have to trickle down. And then you may provide login credentials and then you process the request. Right? So there may be many different ways interactions will occur in this system.
I guess I'm just saying, like, as the definition is, there's no request there ever.
Yes, at the moment not, but that's not excluded. Right? So I mean you can basically have jobs here that run periodically and say which pages are accessed frequently, you retrieve them and stick them in a cache, for instance, so that when request comes in, the performance is improved. Those can run asynchronously, no real request have to trigger them. Okay? So there are many ways requests will flow, but the standard constraint is still there, that you only talk to the layers above and below. Okay, any other questions on this? Any question? Okay. All right. So now, although I showed this 3-layered architecture, there are many different ways to implement it. Okay, I just showed you one as the search engine example, was just one way you implement a client-server application. So there are always 3 things you need to worry about: the interface, the processing logic, and what the data layer, which I would refer to here as the database. Okay. Now you can partition this functions between the client and the server in many different ways. So the dotted line here, okay, that's basically the sequence of example showed on this. So each of this is an example of implementing your layered architecture. Okay, the dotted line is essentially the boundary between the client and the server. Everything that's above the dotted line runs on the client machine. Everything that's below the dotted line runs on the server machine. In most cases, you basically have what is on the leftmost side. Okay, that are not most cases. The common case, which is web-based architecture. Okay, not all So client servers have to be web based, as you can imagine. There are many client server architectures that don't use browsers or don't use the web at all. But when you are in the web world, this is a common way to implement your client server application, which is that what runs on the browser is essentially some user interface code. This could be JavaScript in your browser, for instance. Okay? There's some part of the interface that runs on the server. The processing and the database always resides on the server. Okay? But you could also implement it such that all the interface part just resides on the client side. Okay? And that interface simply makes a call to the application in this case. Okay? If you have a let's say mobile app, for instance, the mobile app may communicate with the server over RPCs. Okay? All of the interface in the mobile on a smartphone is actually on the client side. Okay? There is no user interface processing that is done by the server. The server is simply getting RPC or RMI calls. There's an interface, RPC interface you're exposed. You're just receiving RMI calls and you simply start doing the processing. Okay? Another way to, so this is how many smartphone client server, this is what you see in many smartphone client server world. This is sort of browser based. Okay? Now you can basically keep progressing. So here the third scenario is where the application itself, the application processing layer is split. A part of it resides on the client. The user interface is completely at the client. Part of the application sits here, part of the application sits here, the database sits here. Okay. Now you can have the entire application sitting here with only the database, and then you can, the last one is where part of the database sits. Okay, if you move the entire database there, you are no longer in client server world. You are essentially, everything is sitting on the client. It may be distributed, but everything, all the components are on your machine. Okay. Now if you have, so giving some other examples, in this case, so if you have offline Gmail or offline webmail where your entire data is actually fetched and cached locally, okay, you may sometimes be in this either this or this mode. Okay, because you basically have this notion of offline email. The mail gets downloaded, you can do things locally while being disconnected. Later on, you are resynchronized. Okay. So when you are disconnected, you are in this mode. When you are connected, you might be operating in this mode. Okay, so the same application may operate in different mode depending on what you are doing. Okay. Now it is up to you, the application designer, to figure out where to draw the boundary. There is no a priori right or wrong. It depends on what you are trying to implement. Okay. So you have to think, what is it that you want to put on the client? What is it that you should put on the server? Okay. And why? Okay. The more functionality you push on the client has to do more work, more processing. The more functionality you push on the server does more work, but there better be good network connectivity, because a lot of the work is happening on the server, so there may be frequent communication between the client and the server. Okay, so you have to make the right design choice. As we will see, different applications make different design choices or draw the boundary at different places. Okay, I already give you 2 or 3 different examples. Any questions on this? Okay, so just wrapping up all of that discussion, here is your 3-tier application. Okay, so user interface, application, database, server. Okay, so you have requests coming in. So then you do some processing at the interface level. You hand off the request to the application logic. Application logic does some processing, makes queries to databases. Database query processing occurs. Results are returned. You do some more processing of the results, send the return that result to the user interface layer, does more processing, request close. Okay, this is a very standard way of building your application. I'm going to draw another picture. That's a timeline. Okay, this is the logical flow. Okay, so this could be HTTP. This could be the application logic, which could be J2EE. That could be Tom servlet. This is your DB. Okay, this could be Ruby on Rails if you heard of all of these terms, or Python, Django, any of those frameworks. Okay. So the application is providing a HTTP interface. Okay, so essentially you are going to use a browser. Okay, browser send HTTP request, you do HTTP processing, you hand that off to the application layer. This is where your application is actually written, core of it, okay, what it does. So if this is, let's say, online bookstore, the book catalog is stored in the database. These are the books you are trying to sell. Okay. Processing of requests, whether it's search on a book, buy a book, put the book on a shopping cart, all of those functions are written here. Okay. This is simply HTTP. This just allows the browser to connect to the server. Okay. So this is where you are going to write your application itself. Whether you are using Java, Ruby, Python, PHP, that's not material. That's just the language of choice. But that whatever you are writing, your application code is essentially sitting in the application layer. Okay. So this is your standard 3-tier application. You can have more than 3-tier, but this is just an example similar to your search engine case. Okay. So any other questions here on multi-tier applications? A very common architecture, client server, but the server itself is distributed. Okay, so now we are going to switch to a different type of architecture which is not client server based. These are decentralized architecture. They are also referred to as peer-to-peer or P2P architectures. Okay, in a peer-to-peer architecture, there is, in a client server, you have to realize that we have two types of entities, client and a server. The server is supposedly more powerful than the client. Server implements a service, does more processing typically. Okay. In the peer-to-peer world, that distinction is gone. Okay. There is, everybody is a peer. There is no machine that is more powerful or less powerful. Every machine potentially can do anything. Meaning it can serve as a client at some point or a server at some other point. Okay. So peer-to-peer systems are a different way of designing distributed applications. Okay, you take your functionality, you partition it, and every machine that participates in your distributed application might be potentially called on to do any task. Okay. The client server, typically clients do less, the server does more. The peer-to-peer, you might have to do as much as anyone else. Okay, sometimes more, sometimes less. But typically the way this is built is what is referred to as an overlay network of nodes. What is shown there is a ring-based peer-to-peer architecture. Okay, so peers, the circles there represent nodes, the peers. Okay, peers have organized themselves into a logical ring. Okay. Physically, the network is not a ring. Okay, what this simply shows is that any node is essentially, when you are in a ring, can only communicate with the node before and after it in the ring. Okay, so it's imposing some communication constraint on who can talk to whom. Okay, if this is the constraint, then you are in a ring-based architecture. And now let's think about, let's discuss a little more where peer-to-peer architectures are used. So there are typically, this is used to store and retrieve content, peer-to-peer architecture. So you might take some data items, you can store it, and the different data items land up on different nodes. You come in with queries, and then queries retrieve data items. Similar to what a database does, except that queries in peer-to-peer are not SQL queries. They are essentially what are called key value retrieval queries. So essentially you specify. Right? So peer-to-peer typically architectures essentially allow you to do this. You specify a key. Right? A key is an identifier that identifies a data item, and you retrieve the data item which is returned to you as a value. Okay, so this is what is referred to as a key value store. I'll give you a concrete example. Let's assume you want to implement a phone directory, telephone directory, okay? Online telephone directory, and you want to use the peer-to-peer architecture. Okay? Here is one way you are going to do it. Okay? So basically the main function that a phone directory does is you specify a name. It gives you a phone number. Okay, I want to make sure people are awake. So phone number, give a name, comes a, so key is the name, value is the phone number. Okay, it's simply a lookup service. Specify a name, out comes a phone number. Okay? How are you going to implement that using a peer-to-peer architecture? Let's say there are some n nodes in your system. Okay? First thing you have to do is take the entire phone book and partition it across nodes. Okay? You're not going to store the entire phone book on one machine, and you don't need this. Right? So you're going to say that the job is going to be spread across all the nodes. Each node is going to take responsibility for servicing some requests. So let's say node 1 basically takes all last names beginning from A to C. And node 2 is going to do D to F, and so on and so forth. So you're going to have to partition it into in some way. Okay? The way we are actually going to do it is we are not going to actually do it this way. We are going to take a name and we are going to use a hash function. Okay? This hash function is going to take this name, which is an arbitrary string, okay? And it's going to map it to an integer. Okay? Hash function just takes a name, maps it to an integer, just a function, string to integer mapping. Okay? So we will assume that all the names in the phone book essentially they go when you hash them are going to go from 1 to n. Okay? This is basically simply the output of the hash function. We'll say that given any name, it gets mapped onto an integer range that goes from 1 through n, whatever n is. It doesn't matter what it is. It could be a million, billion, doesn't matter. Okay? So what we will now do is, rather than saying node 1 does A to C and node 2 does D does E to F, we simply say node 1 is going to take all queries that land in the range 1 to I. Node 2 is going to take I plus 1 to J. Node 3 is going to do J plus 1 through K, and so on. So we'll take the integer range or integer name space and we are going to partition it. Okay? So now each node here is going to be given responsibility. So you will see that these nodes are given labels. So that node numbered 1 is basically taking all keys 0 and 1 and it stores those keys. Node 2 is responsible for keys 2, 3, 4. This one is doing 5, 6, 7. This one is doing 8, 9 through 12 and so on. Okay? So the way we are going to now do a lookup is you will take, when a query comes in, it comes as a string, last name. Okay? We apply the hash function. Hash function is going to give us an integer, and we simply route the query to the integer or to the node that is responsible for the integer. So if you look up Shenoy maps to 4, you say which node is responsible for queries or keys that are basically key equal to 4, and that's this node. So simply send the query here. When the query lands up here, it's going to say, give me the record corresponding to hash value 4. Okay? And then you basically take that record, that's the phone number for that person, and you return it. That's an example of how you are going to use a peer-to-peer system. Okay? Now in general, you can have any content. That's the value. In this case, the content was the phone number. But now you can generalize that and say it's any content. Okay, it could be even a file. Okay, this is how peer-to-peer file system or peer-to-peer systems became popular. So it could be a file. Okay, the key is essentially the file name. Okay, so you could generalize this saying rather than having phone numbers and names, you could have some name and an arbitrary piece of content. Okay, so you're always going to take the name, you're going to map hash it, gives you an integer, that's the key. You're going to do a lookup on that key, it's going to give you a value. Value is the content associated with that name, and you return it. So you could essentially look up files. Right? You know, remember that peer-to-peer file systems were popular for storing music files. Content was the file, the name of the song or the file name was essentially the name or the key associated with it. Okay? So in general, it doesn't have to be any particular type of content, it could be any content. Okay? So what I've shown here is essentially a particular type of a peer-to-peer system called CORD. It's a structured peer-to-peer file system. Nodes organize themselves, self-organize themselves in the form of a logical ring. Okay, that's shown there. Okay. Now, the interesting thing is we don't, in this kind of a distributed system, the system is not static. Nodes are allowed to come and leave. Okay, because it's a participatory system. So when a node wants to join this peer-to-peer system, it has to pick a value for itself. Okay, so essentially, nodes are also numbered and so is content. Okay, so this node has essentially picked ID 7 and it joined the ring at that place. Okay, so let's say a new node wants to join, it has to pick a ID that is not used. Let's say it picks 10. Okay, it says my ID is 10 and it joins the ring, so it is going to basically place itself at this point in the ring. Okay. Once it places itself there, then you have to take the namespace and repartition it. So in this case, this node 12 was responsible for all keys from 8 to 12. It will partition its job saying, I'm only going to deal with 11 and 12, you deal with 8, 9, 10, and it's going to send these keys over to 10. Okay. Now 10 basically is in charge of servicing queries that are that map onto that namespace. Okay. And similarly, if you want to leave the ring, at any point you can say, I am done, I'm going to leave this network, you go away, then you reassign the responsibility for the keys you are serving to some other node. Essentially, your neighbor takes over your job. Okay. So the important aspect of the the peer-to-peer architecture is it is built for more dynamism. Okay. The client-server architecture, you didn't have database suddenly saying, I don't want to be part of this system, you deal with something. That doesn't happen. Okay. Machines are static. Okay. Database always serves database query unless it crashes, which is a different problem. But so long as there are no faults, the machines are doing what they're supposed to do. The peer-to-peer system, this is designed to self-organize. Nodes can join and leave at any time. So a lot of the functions in the system are built to sort of deal with coming and going. Machines just leaving whenever they want and so on and so forth. Okay. Yes, question.
So do the links in this particular example restrict the communication between nodes in the sense that if I want to make a query, so do you need to ask my neighbor so that it forwards?
Yes. So question is, how is communication occurring? I haven't come to that yet. That's a very good point. So all I've explained is logically how the key value lookups work and how it's organized. So next point is query comes in, how is it actually going to be resolved? How are you going to do the lookup? That depends on the structure of the network. In a structured peer-to-peer network, which is the form of a ring, communication is restricted to the ring. Okay? You can inject a query at any node, saying, I want to look up. You go to 12 and I say, give me the value for record 0. Okay? So what this is going to have to do is it's going to send it along the ring. Okay, so 12 will send it to, it can send it clockwise or anti-clockwise. So let's say query is flow clockwise. So 12 is going to send it to 15 saying, okay, somehow get this query answered. 15 says, I'm not responsible for 0. I'm going to pass it along and it's going to go to 0. Okay, node 1. Node 1 says, yes, I am responsible for 0. It will basically retrieve that and send it back. Okay. So in this case, communication is structured. There's one way to do it. Another way is you actually find the hash and find the node that's responsible. You can go directly to that node. There are many ways by which communication can take place. You can flow along the ring. You can keep a table which says for every range of queries, who is responsible. You find the IP address and you talk to that node directly. Okay, there are these two. I'll talk about unstructured peer-to-peer where it's done via a different mechanism. Will give me a few minutes. We'll get to that. Any other questions on this? Yes.
Peer-to-peer networks today, they have like a central sort of server or something that has the information of, like the meta information about all the nodes.
Yes, I'll talk about super peers in just 1 minute. Okay, we are coming to that. This is just the basic concept. Okay, we have not done several more slides to go. Okay, so that was one type of structured peer-to-peer network which was called CORD. Okay, essentially, it's a ring-based topology. I'm going to show you another one which is equivalent, which is called Content Addressable Network or CAN. Okay. They are roughly equivalent. The only difference between them is rather than the key being sort of a single integer, in this case the lookup key has 2 dimensions. Okay. Think of it as rather than, so in CORD you basically specify a key which is a single integer, out comes a value. Okay. If you have basically had 2 keys I and j, and that is used to map onto value, then you essentially have a 2-dimensional network. Okay. Now why would you need 2 keys as opposed to 1? Here the answer is it depends on how you are actually allowing me to address the content. Okay. So basically I could say this could be the file name, this could be the file type. If let's say you are trying to retrieve a file. Okay. So you say I need a file with name foo. Okay. This is a MP3 file. Okay. Or you could say I need a file name foo. It's a JPEG image. Okay, both of those files could have the same name, but they're different types of files. So you could say one, so the I is essentially the name of the file, J is the type of the file, for instance. Right? So you are basically are specifying a query with two arguments, saying here is the key and this is the type. You could partition your essentially content and provide it two attributes. And then you can look up on both of those attributes. You essentially have a two-dimensional network. You can have an n-dimensional network. You could say file name, extension, type, or you could say file name, type, date of creation, yet another attribute. Now you have a three-dimensional network. You're saying, find me a file foo. It's a music file. It was created no more than 1 month ago. Okay? Creation time is less than 1 month. You don't want files that are 5 years old. Now your system has to now track three attributes, the date of creation, and you are allowing queries on these three attributes. Okay, so this is showing you two-dimensional, but all I'm trying to point out is you can generalize this to make it n dimensions. Okay, so let's just stick to 2 dimensions for the rest of the slide. Okay, so here this is showing you a two-dimensional space. So it's essentially assuming that your keys are going to go, okay, along each dimension. So here it goes from 0 to n, one attribute, the other attribute goes from 0 to m. Okay. So when you specify a query, you are going to map it. You are going to use two hash functions. Okay. And then you will basically get some integer here and some integer for each of those attributes. So you will take foo, that will give you an integer. You will take this other attribute, do another hash function, give another integer. So you are going to look for content with key I comma j. Okay, and then you retrieve that content. Okay? Yes, no? Yes, okay. So what is this showing you? So this is essentially showing a grid. So every node, every machine that is part of this peer-to-peer network essentially is responsible for all queries that are represented by a rectangle here. Okay? This node here is going to handle all queries that are within this range and this range, along the x and the y axis. Okay? So all queries that fall within those two range are going to get routed to this node, and this node has that content and is going to retrieve it. Okay? So all queries that go from here to here and here to here are handled by this node. Okay? So whenever a node joins this network, it is given a rectangle. In the previous case, you are given a range, single range. You are responsible for keys 10 through 25. Here you are going to say along the x-axis all keys from 10 to 25, along the y-axis all keys from 17 to 34. That's going to give you a bounding box. That's your job. Okay, all requests for that, those keys are going to be sent to you. So whenever you join, you essentially have to be given a two-dimensional region, which is a bounding box for all the queries that you get. Okay? Now, there are some interesting things that you have to deal with here as nodes come and go. A node joining the system is easy. Okay, let's say this is the current state of the system. There are 6 nodes here. Right? A 7th node joins. Okay? And the node has to first pick a value for itself. Let's say it joins there. Okay, so what you do is you will take this namespace and you chop it up into 2. And say this node is now going to deal with the lower rectangle, and the new node that joined is going to deal with the upper rectangle. Okay, and now you're done. Okay. Now nodes leaving the network causes more complications. Okay, let's suppose that this node suddenly decides it wants to leave the network. Okay, now some other nodes have to basically take over its responsibilities. Okay, now if you take this rectangle here, it doesn't smoothly join with any other rectangle to make a bigger rectangle. Right? So for instance, if this node had left, you could have taken all these keys and handed it to this node and its bounding box simply because bigger, it still stays a rectangle. Now if you look at this rectangle here, you can't join it. If you can't join it with this rectangle, that's not a rectangular bounding box. You can't join it with this one or that one. Okay, so if that node leaves, you have to decide who is going to take over its job. Okay, the answer is one node cannot take over its job, because if you do that, then you no longer have a rectangular bounding box, which makes routing queries easier. What you have to do is you have to partition this rectangle into, let's say, 2 parts. You can draw a line here and say this part of it goes there and this part of it goes here. Okay, then you still have two rectangles. The reason you have to keep the bounding box a rectangle is makes easier to figure out who deals with what queries. Otherwise, you have some arbitrary shape. If you are given, I want query comes in saying ij, you don't know who has to deal with it. Here you can simply do range comparisons and say this vertex falls into this rectangle and go there. Okay, so in this form of a network, when nodes leave, things are a little more complicated in terms of which other nodes take over its responsibility. Node joining is not that much of a problem because you can pretty much join any rectangle and you just partition it into two. Okay, split a rectangle into two, it still stays a rectangle. They're giving me two arbitrary shaped rectangles, you join them together, it's not necessarily a rectangle. Okay? The boundaries have to match up for you to do that. So you might have to chop it up into smaller pieces and attach them to a set of them. Okay, yes, question?
All these architectures that can always be replications, so there can be a case where they're all overlapping also, like in God and
Yes, good point. I have not mentioned this. So question is, in all of these cases, there is also going to be replication. So although I showed that these rectangles are nicely partitioned, okay, they are going to be overlapping. That's really the question. So the answer is yes, although I sort of said that this node is only responsible for all the queries within its bounding box, to ensure that sudden departures or failures don't actually bring down the system and make content unavailable, you are going to replicate. There's going to be a primary peer that's responsible for this. But if this peer suddenly decides to leave but doesn't gracefully transfer its content to some other node, then what? All those records, let's say in the phone book, suddenly A to C, all the records are gone, the node is left. Okay, if you haven't replicated that, have kept a backup copy of that data somewhere else, your data is going to be unavailable. So you will always create a second copy. Okay? So in reality, these rectangles or ranges are going to be overlapping, but because we always rely on the primary and the backup copy is not used unless data disappears suddenly, okay, this is how you will route queries. But yes, there will be overlaps. If you allow any peer to answer, then you actually have a more complicated problem. You say there are three peers, they all have a copy of this content. Which one should I pick? Slightly more complicated. So typically, you would say, let's start with the primary. Only if the primary has disappeared will you do something more fancy. Any other questions here? Okay, so I'm going to show you one or two more slides and then maybe continue the rest later. Okay. Unstructured, so everything I said so far is a structured peer-to-peer system. Okay. There are unstructured peer-to-peer system where a node can arbitrarily join a network and then it can pick its neighbors. In this case, a node picks an identity for itself. It picks an ID and it joins at a well-known place. Its neighbors are defined because of structure in the network. You can say that there is no structure. It's a randomized peer-to-peer system where I join a node, I as in a node joins the system and it says I pick 3 neighbors at random and I'm connected to those 3 neighbors. Okay, so you have some so you have some nodes already, they are joined in some arbitrary ways. Okay. A new node joins, it picks k neighbors at random, okay, k nodes at random, and then it says I'm going to basically form these links. Okay, so the nodes will come and join or leave and those links will disappear. Okay. Now that's the structure of the network, which basically says your randomized links. The links go from any node to any node depending on what you pick. And what happens in this case is, since there is no structure, there is no way to properly assign responsibility, saying you are responsible for this range and you are responsible for this range and so on. So whenever you want to access, so you still do a key value lookup. But the way queries are serviced here is through a mechanism called flooding. Okay, that was some of the question that was asked earlier. How are queries query service? So query comes in here, you say, do I have this content with value key value k? If not, I send it to all my neighbors. Okay, I have 3 links, so I'm going to send it to that neighbor, this neighbor, saying, can you service this query? Each of those neighbors does a lookup and say, can I service this query? If answer is yes, we send back a reply. If not, you keep forwarding that query to all of your neighbors. So the query trickles through the entire network using a mechanism called flooding. Flooding essentially means you send it to everyone, you flood the network with this request, you ask everyone. Okay. And then depending on who has it, you will basically get back reply saying these are the nodes that have it. So 2 points to keep in mind in an unstructured peer-to-peer system. Modella, if you heard of it, is an example of what somewhat old peer-to-peer networks still used in some cases. First is the topology is unstructured. Previous case topology is very defined. It was essentially a ring or a rectangular box with neighbors. Here a node can join arbitrary nodes, existing nodes become logical neighbors. Second thing is because there is no structure, you cannot identify which node is responsible as that you are looking for. So the only option is to ask all nodes. You have or ask a large fraction of the nodes, and that is the mechanism called flooding. You flood the query. So there are implications of doing that. Clearly, every request is seen by a lot more nodes. There is more processing to be done. The structured case, you know precisely which node has the content, so you only ask that. So less communication. Here there is more communication, more anarchy in some sense. Okay, so I will stop here. Okay, let me just mention one thing because there is a question there and then I am going to stop. So here is another way to construct this unstructured peer-to-peer system. In unstructured peer-to-peer system, the problem is that all queries are answered to flooding. So every query flows through a lot of unnecessary nodes saying, do you have this content? Do you have this content? So you ask everyone. Right? To reduce the burden of query processing, what often happens is collections of peers come together and elect a leader, saying, you are the leader for this group. Only you should answer. We will tell you what content we have. You construct a table, and when a query comes in, you answer this query. Don't send it to us. So what is shown here is within each group, there is a leader. This is called a super peer. Okay, within this group, that black nodes are super peer for their group. Black nodes keep track of what keys are and values are stored at other nodes. Okay, they construct the directory or the table saying, within my group, this is all the content, and here is who has it. So when queries are flooded, they only go to the super peers. Only super peers actually answer queries, and then content is retrieved from the individual peers. But trying to figure out who has it is only done at the super peer level. Okay, so you have to dynamically elect within each group a node that is going to be responsible for answering these queries and so on. Okay, so this is essentially imposing a structure onto an unstructured network by electing leaders which are super peers and so on. Okay, just as an aside, Skype uses essentially this form of topology. It essentially uses super peers to figure out who is logged into Skype currently. So if you want to basically make a Skype call to someone, okay, you don't know where they are, right, and whether they are even logged into the system. When you sign into the system, typically the super peer in your group keeps track of that, and then that information propagates to your network, and eventually everyone who has you on their buddy list figures out you've signed in. Okay? This is not done by you announcing to everybody on Skype saying I've logged in. There may be millions of users who are logged into Skype. Okay? You don't know who is your friend, where they are, and so on. You essentially tell that to your super peer propagates that, and then if some of your friends have you in the buddy list, you're going to figure this out. Okay, what that also means is in Skype, you have to essentially figure out who is your super peer. You might have to elect super peer. If you are on well-connected, sort of on a high bandwidth network, Skype may elect your Skype client to become the super peer for a small group. Suddenly you see Skype traffic coming in if you are actually looking at network, even though your Skype client is sitting there idle. This is because you become a super peer within Skype, for instance. Yeah, so these kinds of protocols are not just used for content sharing. In this case, you are essentially keeping track of all the users who is logged in, what their current status is. Okay, that's the content. You say this is the username, is this person logged in, and if so, where are they currently? Okay, so that kind of information is also used in peer-to-peer networks. Okay, we have run out of time. We'll stop here for today. Continue the next 2 slides next time.